Hello everyone. We are going to discuss about wave propagations. There are three types of wave propagations: ground wave propagation, surface wave propagation, and sky wave propagation. Ground wave propagation. The propagation of EM wave near the Earth's surface, including troposphere. When the transmit and the receiver antenna are on the Earth, there can be multiple paths for communication. If the transmit and receiver antenna are in line of sight, then direct path exists. The propagating wave is called direct wave. When EM wave encounters an interface between two dissimilar media, a part of energy will flow along the interface known as surface wave. At LF and MF, this is predominant mode of energy transfer for vertically polarized radiation. Interaction with the objects on ground will manifest as reflection, refraction, diffraction, scattering. Waves are collectively called as space wave. In Eloy's model, the assumption is that there is only one path for propagation of EM waveform, transmit antenna to receiver antenna. The two antennas are kept in free space with no other objects intersecting the radiation from transmitter antenna. If two antennas are situated close to the ground due to discontinuity in the electrical properties at the air-ground interface, any wave that falls on the ground is reflected. The amount of reflection depending on the factors like angle of incidence, polarization of the wave, electrical properties of the ground, that is conductivity and dielectric constant. The frequency of the propagating wave, thus the field at any point above the ground is vector sum of the fields due to the direct and reflected waves. Direct wave, it is limited to line of sight transmission distances. The limiting factors are antenna height and curvature of path. The radio horizon is about 80% greater than the line of sight because of diffraction effects. A path of the signal from the transmitter is bounced off the ground and reflected back to the receiving antenna. If the phase between the direct wave and reflected wave are not in phase, it can cause problems. Space wave propagation travels directly without the reflection on ground. Occurs when both antennas are in space wave bends near ground follows a curved path. Antennas must display a very low angle of emission. Power radiator must be in direction of the horizon instead of escaping in sky. A high gain and horizontally polarized antenna is recommended. If dipole and the field points are on the surface of the earth but separated by a distance, we have R2 is equal to R1 is equal to D and psi is equal to 0. If ground has finite conductivity, then it is equal to -1. The EF due to the direct and ground reflector wave will cancel each other. The EF due to the direct and ground reflector wave is also known as surface wave. The surface wave constitutes the primary mode of propagation for the frequencies in the range of few kilohertz to several megahertz. In AM broadcast application, a vertical monopole above the ground is used to radiate power in the MW frequency B, and the receivers are placed very close to the surface of the earth, and hence they receive the broadcast signal via surface wave. The frequency of the electrical properties of the ground over which the ground propagates. At the surface of the earth, the attenuation is also known as the ground wave attenuation factor and is designated as the numerical distance. P is equal to pi r by lambda x cos b, where b is the power factor angle. B is equal to tan inverse r plus 1 by x, where r is the distance between the transmit. And for last numerical distance, attenuation factor decreases by the factor of 10 for every decade, that is 20 dB per decade. Thus, attenuation is inversely proportional to P and R. The electric field intensity due to the surface wave is proportional to the product of A and E by R. The EF due to the surface wave at large distance from vertically polarized antenna is inversely proportional to the surface of the distance, or the power is inversely proportional to RF. The EM of a vertically polarized wave near the surface of the earth have a forward tilt. The magnitude of the wave tilt depends on the conductivity and permittivity of the earth. The horizontal component is smaller than the vertical component and they are not in phase. The EF is elliptically polarized very close to the surface of earth. Tropospheric propagation. The lowest part of the Earth's atmosphere is called troposphere. Typically, the troposphere extends from the surface of Earth to an altitude of approximately 9 km at the poles and 17 km at the equator. This upper boundary is referred to as the tropopause and is defined as the point at which the temperature in the atmosphere begins to increase with height. Within the troposphere, the temperature is found to decrease with altitude at a rate of approximately 70 per kilometer. The Earth's weather system is confined to the troposphere, and the fluctuations in the weather parameters like temperature, pressure, and humidity cause the refractive index of the air in this layer to vary from one point to another. It is in this context that the troposphere assumes a vital role in the propagation of radio waves at VHF 30 to 300 MHz and UHF 300 to 3000 MHz frequencies. The meteorological conditions therefore influence the manner in which the radio wave propagation occurs in the troposphere, both on a spatial and temporal scale. Skywave propagation. Medium and high frequencies of 2 to 30 MHz reflection from the ionized region in the upper atmosphere is called ionosphere. Ionosphere act as reflector surface more than 30 MHz and not reflector and penetrate into ionosphere. The reflection from the ionosphere called as ionospheric propagation, suitable for 2 to 30 MHz called as short wave propagation, and long distance point to point communication called as point to point propagation. Structure of ionosphere. Ionization occurs when high energy ultraviolet light rays from the sun enter the ionosphere region of the atmosphere, strikes a gas atom and literally knock on the electron free from its parent atom. A normal atom is electrically neutral since it contains both a positive proton in its nucleus and a negative orbiting electron. When the negative electron is knocked free from the atom becomes positively charged and remains in space along with the free electron, which is negatively charged. This process of upsetting electrical neutrality is known as ionization. The free negative electron subsequently absorb the part of ultraviolet energy which initially freed from their atoms. As the ultraviolet light waves continues to produce positive ions and negative electrons, its intensity decreases because of the absorption of energy by the free electrons and an ionized layer is formed. The rate at which the ionization occurs depends on the density of the atoms in the atmosphere and the intensity of the ultraviolet light wave, which varies with the activity of the sun. Since the atmosphere is bombarded by ultraviolet light waves of different frequencies, several ionized layers are formed at different altitudes. The four distinct layers. The ionosphere is composed of three layers designated D, E, and F from the lowest level to the highest level, as shown in the figure. The F layer is further divided into two layers designated as F1, lower layer, and F2, the higher layer. The presence or absence of these layers in the ionosphere and their height above the Earth varies with the position of the Sun. At high noon, radiation in the ionosphere directly above a given point is greatest. At night, it is minimum. When the radiation is removed, many of the particles that were ionized recombine. The time interval between these conditions finds the position and number of ionized layers within the ionospheric changing. The D layer ranges from about 30 to 55 miles. Ionization in the D layer is low because of its lowest region of the ionosphere. This layer has the ability to refract signals of low frequencies. The high frequencies pass through it and are attenuated. After sunset, the D layer disappears because of the rapid recombination of the ions. The E layer limits are from the 55 to 90 miles. This layer is also known as Kenley Heavenside layer because these two men were the first to propose its existence. The rate of ionic recombination in this layer is rather rapid after sunset and the layer is almost gone by midnight. This layer has the ability to refract signals as high as 20 MHz. For this reason, it is valuable for the communication in the range. The F layer exists from about 90 to 240 miles. During the daylight hours, the F layer separates into two layers, the F and F2 layers. The ionization layer in these layers is high and varies directly during the day. At noon, this portion of the atmosphere is closest to the sun and the degree of ionization is maximum. Since the atmosphere is rarefied at these heights, recombination occurs slowly after sunset. Therefore, a fairly constant ionized layer is present. The F layers are responsible for high frequency long distance transmission. So that's all about wave propagations. Thank you.